with the distance learning and the new AP Chem exam. The AP Chem exam, the date is to be decided. We don't know when that's going to be. There will be 2 dates. You also know that they're going to be only 45 minutes, and this will be take home with open notes as far as I know, and hence I am doing this video so that you can fill in your handout along with me. There will be no multiple choice, so as we go through this packet, please do not spend time on any multiple choice. You will have free response question worth 45 minutes. We don't know the structure of it. We will know more information after April 3rd. Okay. Now, as for this video, we are addressing big idea 1 and big idea 2. And they have lots of concepts. Major concepts are mass percent, empirical formula, molecular formula, hydrates, purity. Then we talk about electron configurations. Then we talk about PES. We talk about periodic trends and alloys. Then we talk about, this is all big idea 1 still. Then we talk about mass spectroscopy. We talk about spectrophotometry. Then we talk about titration. Not really. I think this is phased out. Then we talk about big idea 2, and under big idea 2, we talk about states of matter, particulate level drawings. Then we talk about gases, solutions. Then we talk about separation of mixtures, specifically chromatography. We talk IMFs. We talk chemical bonding. Then we talk Lewis structures and VSEPR and hybridization. And I'll try to do all of that within 45 minutes with a timestamp video. So the structure of that is going to be like this. This is a packet that you have. These are the big ideas and the big topics on the first page. Now, you will be watching this video and I will attach College Board PowerPoint. So here you're pretty much doing everything except for titration, which we can get rid of. And you will be watching the College Board PowerPoint and you will be taking notes in these boxes as I'm going through this lecture, this video lecture. Okay, so fill out your notes, because if your test is open notes, it's very important to have good notes with you. Okay. All right, and then at places, I will say pause the video now and go do free response question, let's say 2019 number 2. So you will Google, go to College Board AP Chem free response 2019 number 2, or just Google 2019 and do problem number 2. So the way I am envisioning this video is I'm going to go over certain concepts. Then I'm going to give you a question from College Board that you can search on the web and get to. Take a pause and see how those concepts are applied. Then move on with the video. All right. So here goes. Okay, I have lots of papers that you know about me. I'm a very visual learner, so I will be using a lot of them. Okay. So the very first thing is law of constant composition, and generally mostly at the particulate level. Law of constant composition applies only to pure substances like compounds, and it says that any pure compound has the same ratio of masses of elements. For example, in water, oxygen and hydrogen are in 16 gram to 2 gram or 8 to 1 ratio. And if it is pure water, no matter where it is from, the ratio of masses will be the same. And just reminding you about different types of substances, pure substances and mixtures. And pure substances were elements or compounds, and elements are simplest units of matter that have their property, and then compounds are combination of elements, but they are in the same ratio. Then there are homogeneous and heterogeneous mixtures. Remember, mixtures have variable composition. In a homogeneous mixture, every place of the mixture has the same composition, while a heterogeneous mixture does not have the same composition throughout. Mixtures can easily be separated by physical means, while to separate pure substances like compounds into their elements, you have to use harsh chemical means. Moving on from there, the next thing I want to talk about is mass percent. Mass percent is mass of any one component, either in a molecule or in a mixture, overall mass of the whole compound times 100. And these things now, by now, you know, are hydrates, where we put as .5H2O. That means a plus. So in figuring out the molar mass of this compound, you add 5 water molecules to this. And then you can do a problem from the summary notes, or you will be using it later on. So just hang on right now. The application of mass percent was in Green Chem Lab, and I'm going to talk about Green Chem Lab in a few minutes from now. Now I'm going to move on to empirical formula, molecular formula, and hydrates. And I have a little bit more detailed and colored notes here. Let me start with hydrates. Hydrates are compounds that have water molecules physically attached to them, in this case .5H2O. Hydrates, to figure out the formula of hydrates, what you need to figure out, in 1 mole of a compound, how many moles of water are present. So really, in 1 mole of a compound, in the entire compound, how many moles of water are present. And to do this, what you do is you take a crucible, you take hydrate, you drive off the water, and then get how many moles of anhydrate is there, how many moles of water, and then you calculate the moles of water in there. The thing to remember for hydrates is you round moles of water. This is an important thing to remember here. So if you get 3.66 moles of water, you notice 4 moles. So the rounding rules apply here. For empirical formula is defined as the smallest whole number ratio of moles. Here you do not round, but you use a multiplier, okay, to get a whole number. So in empirical formula, you do not round. You can calculate empirical formula from mass percent or from combustion data. When you do it from mass percent, first thing you need to remember is to convert the percents into grams. So assuming 100 grams of compound, these percents will become grams. Then you divide each by their molar mass, and then you get number of moles. The place where you often forget is divide all of the moles by the smallest number of moles. And then if you get a whole number, no problem, then that is your empirical formula. If you don't get a whole number, then use a multiplier. Please do not round. You can round for hydrates, you cannot round for empirical formula. Second way of finding empirical formula is from combustion data. And again, you can have 2 types of problems in there. Remember, the experimental setup was you take a known amount of a compound, you pass oxygen gas over it, and then you have 1 U-tube, and inside here you have carbon dioxide absorbing material, so it absorbs carbon dioxide. Then you pass it through another tube, that is water absorber, so it tells you how much water is absorbed. So ultimate data you have is how much carbon dioxide and water are formed. And in a compound that is made up of only carbon and hydrogen, when you react it with oxygen, all of the carbon will get converted to carbon dioxide, all the hydrogen will get converted to water. And from grams of carbon dioxide, you can calculate moles of carbon. From grams of water, you can get moles of hydrogen, and then divide both by smallest moles, whichever are the smaller moles, carbon or hydrogen. And if you get a whole number ratio, then that's your empirical formula. And if you do not get a whole number ratio, then you need to use a multiplier. Things get a little bit more challenging if your compound has carbon, hydrogen, and oxygen, because this oxygen is present within the compound. and then you're pumping some oxygen from outside, so you don't know which oxygen is this. So to get the amount of this oxygen, you have to add one more step. So from grams of carbon dioxide, you get grams of carbon, also moles of carbon. From grams of water, you get grams of hydrogen, also moles of hydrogen. If you add grams of carbon plus hydrogen and subtract them from total compound, because total compound is made up of only carbon, hydrogen and oxygen, and if from total compounds grams you subtract grams of carbon and hydrogen, then that will give you grams of oxygen. And from grams of carbon, hydrogen and oxygen, you can get moles of carbon, hydrogen and oxygen, divide by smallest moles, and then you get the empirical formula. Sometimes you may be asked to calculate molecular formula, and for calculating molecular formula, they have to give you molar mass. Then you take the molar mass and divide it by empirical formula mass, and it will give you a small multiplier or n. And if you multiply your formula by n, you get molecular formula. In some instances, like in water, empirical and molecular formula are the same. You can simplify it further. So this is both empirical formula and molecular formula. But if you had C6H12O6, its empirical formula will be CH2O, but its molecular formula will be C6H12O6. And hydrates we have gone over already. And at this point, there are many questions, but the one I have is more about moles and mass percent. Can you please at this point do 2016 number 3 A and B? You can find it online, so please do take a pause here. Please do 2016 number 3 A and B. This is more on moles rather than empirical formula, but at least it tests you on something related to that. Okay? Unpause the video once you are done with 2016 question, and you can find that question by Googling it. Hopefully you did the question. Welcome back. And the next thing I'm going to talk about is percent purity. And at the end of percent purity elements, I would like you to do 2018 number 3 G, H and I, not A, B, C, D, E, F, but G, H and I part, okay, at the end of it. So percent purity, oftentimes chemists dig things from the ground, or the metals come as ores that have impurity in them. So oftentimes we need to find purity of a sample, or we need to purify it. So percent purity is an important concept. It is grams of desired sample or desired part of the sample over grams of total sample times 100. And a typical problem on this will look like they will give you an impure substance. Remember, not the entire sample will be that substance. Only part of that will be the desired substance. Rest will be impurity. For example, let's say our desired substance is iron, but it has impurity too. And the problem will have you react, say oxygen or something else, with either the desired or the impurity. Generally, it's with the desired substance. And you know here that your impurity doesn't react with oxygen. So whatever Fe2O3 is formed comes exclusively from iron here. Then they will give you grams of Fe2O3, and you can get moles of Fe2O3. So you can get moles. From moles of Fe, you multiply by molar mass, get grams. And if you divide the grams of Fe by total amount of substance, which they will need to give you with original impurities in it, times 100, then that will be the percent purity of the sample. And then they can give you, I think this is 2018 question that I've done here. So take a pause and see if you can do that question. But the concept is grams of desired sample over total sample. Another type of questions that are often asked on percent purity is like calcium carbonate based questions, like 5 grams sample of calcium carbonate that is impure, right? And then they say it is reacted with HCl and it makes some gram. I'm just making up these numbers, so it might be a negative number, I don't know. It creates 2 grams of carbon dioxide. What is the percent purity? Now, you should know that calcium carbonate, when it reacts with HCl, hydrochloric acid, forms calcium chloride plus H2CO3, which breaks up into H2O and CO2. So the only thing that whatever carbon is in the sample gets turned to carbon dioxide. So from moles of CO2, you can get moles of CaCO3, and that you can turn to grams of CaCO3, and if you divide it by total grams times 100, you get percent purity. So the basic idea here is one of the components, generally the desired component, they will selectively react with something that only reacts with that, and then you find percent purity. Please take a pause at this time and do question 2018 number 3 G, H and I and check for your understanding. Alrighty, I'm going to move on with separation techniques. And separation techniques, there are very many, but the ones we are going to focus on is distillation, chromatography, mostly actually chromatography. Chromatography is a method where compounds are separated based upon their solubility either in a stationary phase or on mobile phase. So typically you can have paper chromatography, gas chromatography, liquid chromatography. They are named such for their stationary phase. So when your stationary phase is paper, we call it paper chromatography. And generally paper is non-polar. And then you will have water in there or a polar solvent. And as you put a mixture of inks, the part of the ink in that mixture that dissolves in water more. As the water rises up through this paper, the part of the ink that dissolves in water more or is more polar in nature will get separated out. The one that is less soluble in water or likes the paper more will get left behind. Note that they can switch their mobile and stationary phase, so don't assume, pay attention. Which is your stationary phase, which is your mobile phase, and is your stationary phase polar or non-polar, because that can change as well. And the question you can do at this point is 2017 free response number 4. Please pause the video here, do 2017 number 4 and come back to me. And this is the question, so please do that. This will reinforce your concept. Okay, welcome back, elements. Now we're going to talk about electron configurations, PES, periodic trends, and alloys. So electron configuration, remember how to write these configuration. You just go with the Aufbau's principle. If it is an excited configuration, then you will not follow Aufbau's principle as such. Like instead of 3s2 3p6, it could be p5, and 4s2 3d6 3d10 4p6, and 5s1. So even though this p is not filled, it could have filled, jump this electron to 5s. The telltale sign of excited configuration is number of electrons are the same, whatever are present in atom. How it is different from a cation or anion configuration? In cation, there are lesser number of electrons than the atom, and anion has greater number of electrons than the atom. And as you make the cation, remember the farthest electrons are removed away first. So 4s goes before 3d. So if you think of this as nucleus, first energy level, second, third, and fourth energy level, then the 4s electron being farther out will be removed before the 3d, even though 3d has higher energy. So if we go take a minute and write copper and copper plus 1's electron configuration at this point, and I don't have it handy with me, but copper anyways is an exception, so it is S1D10 if I'm not wrong, or it is S1D5. I don't have a periodic table handy, but what I'm trying to say here, this s electron 4s will be lost before 3d. So you will have S0. It could be D5 or D10. I don't know, copper and chromium. I think it's D5, S1D5. So it'll be S0, 3D5. You don't have to write S, but know that those will go first. Then when talking about electron configuration, dia and paramagnetic are important terms to know. Diamagnetic have no unpaired electrons and show no magnetic property in the external field. Paramagnetic have unpaired electrons. This is photoemission spectroscopy. Using this technique, you can knock off any electron and figure out how much energy was this electron experiencing from the nuclear proton, or how much attraction was any one of these electrons was experiencing from nuclear protons. And it is not the same as ionization energy, because ionization energy applies to the outermost level electron. If you wanted to figure out how much energy will be required to remove this electron, that won't be ionization energy. So photoemission spectroscopy is an evidence for Bohr's model, where we say 1s electrons have the least energy, then 2s, then 3s, and so on. This gives an evidence for Bohr's model of atom, or quantum mechanical model. Okay, so what you notice here, note the x-axis. This is highest energy and this is lower energy here. So these will be the innermost electrons, because this is measuring binding energy. It's not measuring kinetic energy elements. This is measuring potential energy. So the innermost electrons experience most attraction from the nuclear proton. So they will have the highest binding energy or highest potential energy. However, the first, second, third energy electron will have higher kinetic energy. But in PES, we are writing binding energy or potential energy. Okay, so if you see that this will be 1s2, 2s2, and then you use the ratio. The height of the peak shows you number of electrons. So 1s2, 2s2, then this will be 2p3, because it's a third higher. So then you can figure out what electron it is, what atom it is based upon the electron configuration, or given the PES spectrograph, you can figure out what element it is or what ion it is. Okay, for PES question elements, you can do 2018. After PES, please pause it here. Do 2018 number 7. AP Chem free response. Okay, and check your answer with the key. This is for PES. Please do the question, then come back to me. Okay, welcome back elements. Hopefully PES went well for you. Now let's explore periodic trends. Remember, the periodic trends are the ones that repeat themselves across a period. The first and foremost is atomic radius decreases across a period and increases down a group. That's because effective nuclear charge increases across a period and increases across a period, which results in smaller atomic radius. Effective nuclear charge is defined as attraction of outermost electrons by nuclear protons. Whatever attraction the outermost electrons are feeling from nuclear protons is called effective nuclear charge. Across a period, you have same number of shielding electron but increased number of protons. And the formula here for calculating E and C is number of proton minus number of shielding electrons. So your number of protons are increasing as you're going across the period, but your shielding electrons remain the same. Hence, your effective nuclear charge increases across a period, decreasing the atomic radius. However, when you go down the group, what is causing increased atomic radius is increased number of energy levels, because as you add more energy levels, electron-electron repulsion increases and atomic radius increases. Then ionization energy and electron affinity are opposite of atomic radius. So as across a period atomic radius decreases, ionization energy increases. Ionization energy is defined as the amount of energy required to remove the outermost electron from an atom in its gaseous state. So if you have atom A in its gaseous state, to remove an electron from it and make a cation, whatever amount of energy is required is called ionization energy. First, ionization energy increases across a period because the atomic radius is decreasing, and decreases down the group because atomic radius is increasing. Second, ionization energy, which is from a cation, you remove another electron in its gaseous state, will always be much higher than the first ionization energy because you're removing an electron from a cation. Now elements, there are two exceptions to ionization energy. So I just told you that ionization energy increases across a period, right? So as the atomic radius becomes smaller, ionization energy is increasing. However, there are two exceptions. First exception is between group 2 and group 13. Second exception is between group 15 and group 16. And let me talk about it. So ionization energy increases here, here, and then it decreases in this group. Here the electron configuration is s2p1 while it is s2. Here the electron you're removing is from p sublevel versus the s sublevel in group 2. Remember, p electrons do not penetrate the nuclear region the same way the s electrons do, or p electrons do not experience nuclear attraction the same way that s electrons do. That is why ionization energy for group 13, where you're removing a p electron, is lower. The second exception in ionization energy is between groups 15 and 16. Between group 15 and 16, when you add electron, in group 16 you add electron to already occupied orbital, right? It's 1, 2, 3, and then the fourth electron goes here. If you are trying to remove this fourth electron, it will take little lesser energy due to electron-electron repulsion. Okay. Then let's talk electron affinity. Electron affinity is amount of energy released when an electron is added to an atom. Then whatever amount of energy is released, that is called electron affinity. And because it's energy release, there's a negative sign to it. Negative is a direction of energy release but not a negative number. So negative 50 is still higher than negative 5. Okay, generally the unit of electron affinity is kilojoules, And the way we gauge it is with E. E is proportional to Q1, Q2 over R squared. So the larger the size of an atom, the lesser the attraction the electron will feel from its electrons. Okay. And electron affinity again increases across a period because electron affinity increases across a period because atomic radius is decreasing. However, there are two exceptions. First exception is between group 1 and 2 here. That's because when we are talking electron affinity, in this one, we are adding the second electron to 1s1 because there's only one electron, we're adding it to s. But when you talk about adding another electron to the second element here, s2, you are adding to the p sublevel. And because p sublevel electrons are not attracted by the nuclear region the same way the s electrons do, hence electron affinity goes down between group 1 and 2. The other change or decrease in electron affinity exception is between group 14 and 15. And the reason is when you're adding an electron, there is p1, p2. When you add another electron, it goes in an empty p sublevel. But when you add an electron to an element in group 15, it is already p3. So you're adding that electron in an already filled or occupied orbital, and there will be a certain repulsion from the existing electron on the incoming electron. So its electron affinity will decrease a little bit. Remember, repulsive forces are with positive sign, attractive forces are with negative sign. And at this point, elements, I suggest that you take a break, please, and do 2018 free response questions number 3, A and B. Okay, number 3, A and B. Please pause the video and come back to me. The next thing I want to review with you is mass spectroscopy. Mass spectroscopy is a technique where you take an unknown sample and whatever bonds you have in there, you randomly break it. You hit them with electrons and they randomly break those bonds. So you get different mass fragments in there, and what you get is a mass spectrograph. On the y-axis is percent abundance and on x-axis is the mass in AMU. If it is a pure element, and in our curriculum we are only talking about elements, so if it is an element and you're getting 3 different peaks, what it tells you is there are 3 isotopes of that element, because isotopes still have the property of the same substance but they have different mass. So this tells you they have 3 different isotopes. And then you may be asked to calculate average atomic mass. You take decimal fraction of percent abundance, multiply it by the atomic mass of that fragment, then do the same for the second and third using this equation. A decimal fraction of 30% is 0.30 times 6.02, 0.40 times 6.95, and so on, and that helps you calculate average atomic mass. Another thing you can do from mass spectrograph is figure out if a substance has a pure sample, is a pure sample or not, or is there an impurity. So you can run spectrograph of a pure sample, right? And then you can run spectrograph of the sample provided to you. If you have extra peaks in there that don't belong in the pure substance, then you know that there is something else in there. Now I would ask you to look at a practice problem from your handout, or from, if you Google it, you will see so many practice problems on mass spectroscopy. Just Google mass spectroscopy AP Chem and you'll come up with a lot of problems. Please do a problem on mass spectroscopy. And let's move on to a very small topic of rotational, vibrational, and translational energy, and E is equal to h nu. So rotational energy or rotational motion is connected to least energy because it's the smallest motion. Vibrational is a little bit bigger motion and has a little bit larger energy associated with it, and translational is motion is associated with electron transitions through different energy levels and generally has pretty high energy associated with it. And we can calculate energy using E is equal to h nu. This equation and the values of Planck constant are given in the equation sheet. E is energy, its unit will be joules or kilojoules. H is Planck's constant, its value 6.63134 times 10 power negative 34 joules per second. It is given in your equation sheet, and nu's units is frequency and its unit is 1/second. Another equation you need to remember is C is lambda nu, where C is speed of light, lambda is the wavelength in meters or nanometers, and nu is frequency in seconds. Okay, now we're going to get to colorimetry or Beer-Lambert's law. So Beer-Lambert's law is simple as A is equal to A, B, C, where A is the absorbance, lowercase a is absorptivity constant, B is the path length, this is the length of the cuvette through which the light passes, and C is the concentration of colored species. Beer-Lambert's law can be used in colorimetry or wherever you're trying to measure the concentration of any colored species in a given solution. And how you do that, we've done a couple of labs on that. We did a spectrophotometry lab in first semester, and then we did CV lab in the second semester, and I'll go over them in a minute. But absorptivity constant depends upon the wavelength at which you are measuring the color and the material that the cuvette is made up of. So if you use the same cuvette and the same wavelength, then A becomes constant, path length is constant. So for a given experiment, absorbance becomes directly proportional to the concentration of colored species. And the way we figured the concentration of colored species is we plot a standard graph between the known absorbance and known molarity. Known molarity, and we plot its absorbance, you get a linear regression, and then if you put your unknown solution at the same wavelength and measure its absorbance, then by extrapolating you can figure out what is the molarity of unknown substance. Also, you can take the slope to be A times B, and you can divide the absorbance by AB or the slope to get C. There are few errors that are asked in this. They often ask, what if there is a hair on the cuvette? Then you will get a higher value because the hair on the cuvette will be counted as the color absorbing species absorbed it. What if there is an air bubble? You will get, again, this time you will get a lower absorbance because light will pass through the space that is occupied by bubble and not colored species. So you're letting more light in, resulting in lower absorbance. From there, I'm going to move on to law of conservation of mass. And here, I mean, you know the law, it is that mass is neither destroyed nor created during a reaction, it's conserved during a reaction. You can show it through particulate level drawings, and that is your law of conservation of mass. From there, I'm going to go to Gravimetrics, and Gravimetrics, give me a second here, I have lots of my notes. And before I move on to Gravimetrics, I would like to reiterate this graph. You have it in your packets elements. This is a nice handy dandy summary chart of all of the keywords, because as you tackle the periodic trends problems, keywords are very important. So please find this. If you don't have it, email me. I will give you this graph, this table. So gravimetrics elements is a technique when you mix two solutions, create a precipitate or a solid. Because we can see the precipitate, we can dry, we can filter it using filter paper, pre-weighed filter paper, dry it, weigh it, do analysis like get the grams of precipitate, and if we know what precipitate is that, then using mole ratio we can figure out how much of the substance was present. A common type of problem here could be we have PbCl2 mixture with, let's say, K2CO3 solution, right? We don't know how much of each is present, but we know PbCl2 precipitates selectively with sulfuric acid and it forms PbSO4 precipitate, and KCl doesn't form a precipitate and PbCO3 could form, but imagine it doesn't form, right? Or let's say it's not K2CO3, it's got an impurity. We don't know what that is. But we know for sure that lead chloride, when reacted with H2SO4, forms a PbSO4 precipitate, and it will form HCl also, but we're not concerned about that. This is a precipitate. We filter it out and we dry it. Then we can get grams of PbSO4. We know the molar mass of PbSO4. We can convert it to moles of PbSO4. And we know in 1 mole of PbSO4, there's 1 mole of Pb. So we can get mole of Pb. And in 1 mole of PbCl2, you have 1 mole of Pb. So whatever are the moles of Pb will be same as moles of PbCl2. And from there we can get molarity if they've given the volume, or we can convert it to grams. So this is a typical gravimetric problem, and I expect they will give you experimental problems, but as we do free response questions, you will see that these will get answered. I'm not going to pay attention to titration. You know enough of titration to field any questions that may come your way. And now we are officially at big idea 2. So this was all big idea 1. And at this point, I would like to go over the labs of big idea 1. Then I'm going to move on to big idea 2. The labs of big idea 1 elements, and you might want to grab your lab handout at this point. Take a pause and get your lab handout. In the first semester we did quick egg with big idea 1, it is quick egg relief lab, and then we did green chemistry lab, and we did titration, but I'm going to skip titration, and then we did PES lab. I'm going to go over that. Okay, so with big idea 1, green chemistry lab, the idea of green chemistry lab was to figure out what was the mass percent of a mixture of NaHCO3 and Na2CO3. If you recall, both of these were white solids. This was a white solid and this was a white solid. So we didn't know what is the percent of each one of those, and that is our task. What we know is when you heat the mixture strongly, only NaHCO3 gets converted to Na2CO3, CO2 and H2O. Na2CO3 remains unchanged. So we take a crucible, we purify a crucible, take some mixture in there, weigh it, and then we heat it strongly. When we heat the mixture strongly, carbon dioxide will escape, and the data we need is mass of empty purified crucible, then mass of empty crucible purified plus unheated mixture, and the third data is mass of crucible plus heated mixture. For calculation, you subtract from the third reading second reading. So you will subtract from second reading, you'll subtract the third, because third will be lesser because you've heated the mixture, so carbon dioxide has escaped. So this will give you carbon dioxide and water. Elements both escape, carbon dioxide and water, but they both go X and X. And now we know how many total grams of CO2 and H2O have escaped by subtracting third from second. We know that mass of CO2 is mole times molar mass of water, and mass of H2O is mole times molar mass of CO2. And using this formula, we knew that CO2 and H2O react in a 1:1 mole ratio. Hence, these 2 moles will be equal. And then we put x times 18 plus x times 44. Or if you divide this mass by 18 plus 44, you get x value. And then, because the x is the amount of CO2 and H2O, and the ratio between CO2 and H2O and Na8CO3 is 2:1, we'll multiply the x by 2 to get grams of Na8CO3. Okay. And if we divide the first empty crucible from crucible plus unheated mixture, then we get grams of total unheated mixture, and this will be mass percent, okay, of Na8CO3, and then you can get mass percent of Na2CO3 as well. So this is Green Chemistry Lab. Take a minute, pause it here, and think about what you did, how you did, and what are the common sources of error in this lab. Titration, I'm going to skip, you know enough of titration to get by in case a question or two comes, which I doubt. Okay, the next lab that I want to do with you is Beer-Lambert's law, colorimetry. And in Beer-Lambert's law, our purpose in the first lab was to find the molarity of an unknown blue dye, and we made standard solutions of known molarity, micromolarity, and then we measured their absorbance on the y-axis and created a standard graph, and then we put the unknown, found its absorbance, and using the graphical method then found the molarity, or divided the absorbance by the slope, and that gave us the molarity. Here the common error analysis is what if there is an air bubble, what if you have your fingerprints or something stuck. In this case you will have a lower absorbance or lower concentration. Here you'll get a higher concentration or higher absorbance of color absorbing species. One lab that we just did as a demo was Qualitative Analysis Lab, and this is to find the presence or absence of a certain ion in a solution. So we picked a reagent. Reagent was a solution that forms a precipitate with that ion, and then we did a confirmatory test, another test to make sure indeed it was that. For example, we took lead nitrate and added HCl to it, and if a precipitate formed, we knew that it could be lead ion. And we know that lead chloride precipitate, upon heating, it dissolves. So we heated it, and when it dissolved, it turned into its ions. So that was the confirmatory test for lead chloride. Here, particulate level drawings become very important elements. When you are drawing ions or dissolved, then ions are separated. Mole ratios are important as well. If you are drawing the precipitate, it should be at the bottom. You can draw the precipitate as PbCl2 or Pb, Cl and Cl attached together. Remember to attach Pb in the middle and 2 Cls on the side. Always remember like charges repel each other, so you can put 2 negatives together. Okay, and a common error in this lab is contamination. Then the next lab I want to go over is Quick Ache Relief Lab. And Quick Ache Relief Lab, we had a challenge. This is about intermolecular forces, so really it goes with big idea too. I'm actually going to hold off on this because it was more with big idea. Well, it is mass percent too. Let me address it here. So the scenario was, there was a pill much like your Tylenol. This was called Quick Ache pill, and the problem was that these pills were chipped. So the CEO of the company went to a scientist team and said, why are these pills being chipped? Because then consumers won't buy it. And one team of scientists said pills are chip because the binder ratio is off. Another said no, binder ratio might be off, but that's not causing the chip. A contamination of acetyl salicylic acid or ASA is causing the chip. So our task was to separate the three compounds from quick ache relief: the binder, its active ingredient, which was acetaminophen, and the contaminant, which is ASA. Now, what we knew is binder, we first crush the pill and put it in ethyl acetate. Both acetaminophen and ASA, the contaminant, dissolve in ethyl acetate, but the binder remains behind. So we separated the binder through vacuum filtration to make it go faster and weighed it. We separated on a pre-weighed filter paper, dried it, and then weighed. So that gave us the amount of binder. Then we put some sodium carbonate or aqueous layer. Now, even though acetaminophen and acetyl salicylic acid were both soluble in ethyl acetate, when we added sodium carbonate, or what solution did we use? I think we used aqueous layer, right? When we added NaHCl, the sodium hydrogen carbonate aqueous layer, ethyl acetate dissolves more in the organic layer of ethyl acetate, and ASA, acetaminophen, acetaminophen dissolves more in ethyl acetate, and acetyl salicylic acid or ASA dissolves more in aqueous layer. So then we pour out and separate the two layers, and because the aqueous layer cannot be evaporated, we add HCl to it, and that separates. If there is ASA, it precipitates ASA out, and you can filter it on a dried pre-weighed filter paper and weigh it. That gives you the amount of ASA or contaminant. Now, ethyl acetate containing acetaminophen is yet another layer, and in that layer you evaporate ethyl acetate, then you get acetaminophen. So in this, then you get all the three masses. So you have the mass of the binder, you subtract mass of filter paper from there. Then for acetaminophen, you take mass of beaker plus acetaminophen and subtract the beaker mass from there. And for ASA, you take mass of dry filter paper plus ASA precipitate and subtract the mass of filter paper, and take mass of any component and divide by total times 100 gives you mass percent. Remember, couple of sources of error. Your filter paper may not dry. If it is not completely dried, then you may get a larger mass percent because you will take the mass of water as the mass of precipitate. If you lost precipitate in washing, you will get a smaller percentage. And the last lab that I'm going to talk about here is Hydrates Lab. We use the same method as green chemistry lab. Purified a crucible, put a hydrate, measured the empty crucible, measured the hydrate, heated the hydrate to drive off the water, dried it, cooled it, and then took the difference in the mass of unheated versus heated hydrate. That gives us the mass of water, and then converted it to moles of water. And now we also have mass of anhydrate, so we get moles of anhydrate and moles of water, and we find the ratio. Remember, in finding the hydrates, we must round the answer. So in this lab, the error is if you don't heat the hydrate enough, your mass percent of water will be lower because you haven't allowed all the water to go. If you haven't cooled your crucible enough, your crucible is hot, then you will get, if your crucible is hot, it will weigh less, then you will get a larger difference of mass and you'll get a higher mass percent. So these are the labs from Big Idea 1. Now moving on to Big Idea 2 concepts. Wow, this is going to be one long video. Okay, Big Idea 2 we go to states of matter. You should know them at particulate level elements. And now we're going to go to gases straight. Remember, gases are unique because they are compressible, they can expand, they can diffuse. So the theory that explains the theoretical background behind the behavior of gas is called kinetic molecular theory. It says that gas particles are so small that most of the space in gases are empty. The volume of gas particle as compared to overall volume is negligible. Between gas particles, there is literally negligible force of attraction, and the average kinetic energy is directly proportional to the absolute temperature of gas. Remember, we talk about average kinetic energy, average speed, because gas particles are all traveling at a different speed because of the different mean free paths, the path between two collisions. Remember that model? Kinetic energy of gases is given as half mv squared. And remember, the smaller gases will be moving faster at the same temperature if the average kinetic energies are the same. Also elements, remember, this is the only place in chemistry where the mass or molar mass is in kilograms. You tend to forget that, and that causes you to lose points. So if we take this as helium, argon and nitrogen are present at same temperature and they have same moles in there, then helium will be moving faster because it's a smaller gas. So to have the same average kinetic energy at the same temperature, will be moving fastest. Remember Maxwell distribution graph? This shows the speed, the number of gas particles that have a certain speed at a given temperature. Typically, this is your typical bell curve. As you increase the temperature, the graph flattens and more particles have higher energy. If you cool it, it becomes narrower and pointier. So this purple here is the normal bell curve of a gas sample. The blue one is showing higher temperature and the red one is showing lower temperature. Remember diffusion and effusion of gas? The lighter gases will effuse or diffuse faster, and this is called Graham's law of effusion, where rate of effusion is inversely proportional to square root of their molar masses. And there is a very interesting experiment where you have a tube, and in that if you put HCl and ammonia, ammonia is a lighter gas, its mass being only 17 grams, and HCl being a heavier gas, its mass is 36.5 grams. When they combine with each other, they form ammonium chloride, NH4Cl. And that's a white ring. You'll see that white ring form closer to HCl than to ammonia because HCl cannot diffuse or effuse as fast as ammonia. Okay, next thing I want to talk about mixture of gases a little bit. So let's say we have 10 liters of gas A and we have 10 liters of gas B, and then we put them, or we have, let's say these containers are flexible. Okay, we have sample of A, sample of B. If we mix the two, and sample of A is contained in 1 liter flask, sample B is contained in 1 liter. If you mix the two elements, the volume will still be the same because there is so much empty space between the gases that their total volume does not change upon mixing them together. But what will change is the pressure. The total pressure will become equal to pressure of gas A plus pressure of gas B, but their total volume, so volume of gas A is same, volume of gas B is same, and total volume is same as well. Remember, Dalton's law of partial pressure says that the total pressure is equal to sum of partial pressure of gases. Remember, if you mix gases, the volume does not change. Then gas collection over water. We collect gases over water where gases are not highly soluble in water. For example, if you make hydrogen gas, these are important problems. They can give you a gas stoichiometry problem or add a percent purity problem here. So the gas making assembly looks like that. You take solid zinc, you add HCl, where you're adding HCl from should be dipped in HCl, otherwise your gas is going to escape from here. And then the hydrogen gas that is formed goes through this tube, gets collected here over water. But what else gets collected is water vapor. So the total pressure, if the level outside and inside is equal, that means the pressure on the surface of gas here is equal to atmospheric pressure, but that's equal to pressure of gas plus water, because water also has vapor pressure. And this vapor pressure of water will be given to you in a table. It only depends upon temperature, not on amount. So to get the pressure of gas, you have to subtract from atmospheric pressure the water vapor pressure, and then using PV is equal to nRT, you can calculate gas moles from there. And in here you can also be asked to find purity of sample. Once you know moles of gas, you can figure out moles of zinc. Remember elements. When you use PV is equal to nRT here, this N will be for hydrogen and not for zinc. So in many gas stoichiometry problem, you forget and you put directly zinc in Pavnert equation. You cannot. This is ideal gas equation. You can only put gas in here. So talking about gas stoichiometry, there can only be two scenarios. Either the gases are at STP or they are not at STP. If they are at STP, standard temperature pressure, which is 1 atm 0 degrees Celsius, at STP, 1 mole of a gas is equal to 22.4 liter volume. And this applies to all gases. If a gas is not at STP, then the equation we use is PV is equal to nRT or Pavnert. And in case of gases, the R value we use is 0.0821 liter atmosphere per Kelvin mole. Gases are a big topic. And the last thing is deviation from ideal behavior. So in ideal case, we've made two assumptions. One is that the volume occupied by gas particle as a ratio of the overall volume is negligible. And the second assumption we've made is the forces, intermolecular forces between gas particle are negligible, and both assumptions are faulty. Under normal circumstances, yes, maybe you can ignore the volume of gas particle, but most of the gases have non-negligible volume of the particles. As a result of that, the total volume of ideal gas, real gas, is larger than ideal gas. So to make the real gas reflect the volume of ideal gas, you take away a little bit of volume to reflect the ideal volume. In real life, there is some intermolecular force of attraction. As a result, when these particles hit the wall of container, they hit it with lesser force. So to the Pavnert equation, to the pressure, we add a correction factor to account for this loss of force or pressure. You don't need to memorize this van der Waals equation for real gases, but you should know what it stands for. Real gases have lower pressure and a larger volume than ideal gases for the reasons that I just explained above. Okay, at this point, elements, I would like you to pause it and please go to, where is the gases? Just give me a second. We were doing gases. So please do 2017, number 1, A and B for gases. And 2017 number 6 is for solutions. You can get to it a little later. But for now, please do 2017 number 1 A and B on gases. Okay, take a pause. Alrighty, welcome back. Hopefully you paused the video and did the gases question. Let's talk now IMF. We've already done separation. So let's talk IMFs or bonding in general. So types of bonds: ionic bonds, covalent bonds, and metallic bonds. Intramolecular bonding. So elements where Inter and intra are different, are covalent bonding. Otherwise, in everything else, inter and intra are one and the same thing. In ionic bonds, ionic bond is nothing but the electrostatic attraction between a cation and an ion. And their motto is taken, not shared. So when a metal atom who has 1, 2, or 3 electrons in its valence shell meets a non-metal, it willingly gives its valence electrons to non-metal, and non-metals having high electron affinity are happy to part with their electrons and gain electrons. And the attraction that results after that, this attraction is called ionic bond. And you can write it like that, Ca with brackets, empty valence shell, 2 plus, 2 Cl minus, right? And what determines the strength of the ionic bond is lattice energy. Higher the lattice energy, the stronger the ionic bond. And lattice energy is given by Coulomb's law, which is force is proportional to Q1 Q2 over R square. So energy will be Q1 Q2 over R. And because there are two things that decide how much force, attractive force, will be there, if both are changing, then charge matters more than the distance between the atoms because they are very small. Ionic bonded substances are bonded as crystal lattice repeating pattern of ions. They are generally solids. In solid state, they do not conduct electricity, but in aqueous or dissolved state, they are good conductors of electricity. Now, as you dissolve solids in water, they can be either exo or endothermic depending upon the attraction between ion and the water, depending on the net of the 3 steps. The first step is separating the calcium and chloride ion, which always requires energy or is endothermic. Both of these steps, solute separated, solvent separated. Then the third step, when you mix calcium and chloride together, either they'll really like each other or they won't. If they like each other, then large amount of energy is released, then it is exothermic. And if not a lot of energy is released, then it is endothermic. If the ions highly attract each other, then the distance between them will be less and not a lot. Now, covalent bond 101. Covalent bonds motto is shared, not taken. They exist between non-metals. Examples are H2O, P2O5, CO, PCl3. And they could be polar covalent or non-polar covalent. They are generally non-conductor of electricity, mostly gaseous or liquid state. Polar covalent bonds have the electronegativity difference between 0.3 to 1.7. And they have a positive side and a negative side, and they are said to have a dipole. And the dipole moment is a way to measure dipole. You draw an arrow from the positive end pointing towards negative end. Non-polar substances generally are between two of the same one. The electronegativity difference is between 0 to 0.3. So if you have two of the same, they evenly share their electrons. There is no polarity. And there could be a single, double, or triple bond. Remember, single bond is longest but weakest. Triple bond is strongest but shortest. Okay. And coming back to polar covalent bonds, if they are polar molecules, just 2 atoms, then you draw dipole moment like that. If they are more than 2, then you draw individual dipole moments and look at the net. But before you can draw the dipole moment of a molecule, you must draw their VSEPR shape. Okay. And the strength of covalent bond is determined by bond energy. The higher the amount of energy required to break the bond, the stronger the bond is. Their melting and boiling points are lower than the ionic bonds. And remember, most important confusion, like when you are melting iodine or vaporizing water, you're only breaking intermolecular bonds and not the covalent bond. The only time you are breaking covalent bonds in a phase change is if you are melting a covalent network compound. Alrighty, then the next type are metallic and covalent network bonds. Metallic bonds are formed between metal, and these have electron C model, free electrons. Hence, free electrons are attracted momentarily by whichever nuclear cation they are close to. This is called electron C model. That is why metals have high electrical conductivity. They are malleable, ductile. They cannot be broken. You can pull them because wherever they go, because the atomic orbitals are overlapping, they are flexible. They can overlap without breaking. Their melting points are somewhere in between from low to high, and their strength is again given by Coulomb's law, which depends upon the size of the atomic radius, the charge and the size. Again, charge rules the size. And last type are covalent network bond. You need to remember this: silica, SiO2, germanium, silicon, graphite, diamond. They are all connected to each other through a covalent bond. They have the highest melting and boiling points, are most unreactive, and if you are melting these substances, then you are breaking covalent bonds between them. Now let's talk about intermolecular bonds. Those were intramolecular bonds. Intermolecular bonds are ion-ion, which is ionic bonds. We just went over it, right? Then ion dipole are generally found in aqueous solutions where you have ions surrounded by water molecules. So between water molecules and ions are ionic bonds. They are again given by Q1 Q2 over R squared, determines their strength. Hydrogen bond is when hydrogen is bonded to nitrogen, oxygen or fluorine intramolecularly, then the intermolecular bond is called hydrogen bond. So elements, this bond here is hydrogen bond. This bond is not hydrogen bond. This is a polar covalent bond. Please get that correct. These are not hydrogen bond. Between this hydrogen and the other oxygen will be hydrogen bond. Dipole-dipole exist in polar covalent molecules. When their opposite ends attract each other, then these are called dipole-dipole. HCl is one such bond. LDFs are weak temporary bonds that are present in all, but they only become significant in noble gases and non-polar covalent molecules because there no other bond exists. In noble gases, as the number of electrons or the molar mass increases, distortion and temporary polarization increases, resulting in higher LDFs. And if you have non-polar covalently bonded substances, again the same thing applies. With higher molar mass will be stronger LDFs. Few things to remember about LDFs elements. Dipole-dipole. So if you compare HCl, HBr and HI, HCl has the highest electronegativity and HI has lowest electronegativity, right? So the highest dipole-dipole attractions will be in HCl and lowest will be in HI. So if they want you to explain a boiling point based upon dipole-dipole, they will give HCl highest. However, if they want to explain some property based upon LDFs, then HI will be highest as compared to HCl because IA has the most electrons. So you have to kind of read the question carefully. They could be asking you for dipole-dipole based upon electronegativity, but they could also be asking you for LDFs. The next thing you should know about carbon chain. As you increase the length of carbon chain, then the highest IMF exists between longest chain because there is more polarization, right? Now, if you have long straight chain versus branch chain of the same number of carbon, the straight chain will have highest LDFs because of the most polarization. Then, what if you have OH bonds? If you have OH bonds, hydrogen bond effect is the same in all, But as your carbon chain increases, London dispersion forces become more. So remember this, they may ask you some question on this. And if you have same number of carbon atoms but you change your OH, again hydrogen bond increases because you are adding more hydrogen bonds. Okay. Then in terms of solubility of compounds, like dissolves like is the principle. Okay, if you have a polar substance, it dissolves in polar solvent. A non-polar substance dissolves in non-polar solvent. So common polar solvents are water, methanols, anything that has OH, anything that has CO in it. And non-polar substances are CCl4 or oils, things like that. So if it is a non-polar thing, it will dissolve in a non-polar substance. If it is a longer chain versus shorter chain dissolution, longer chain dissolution will be harder because for chains to align and solvent molecules to get in between them will be harder. Okay. Also, if you have OH, a longer chain makes it harder to dissolve in water than a smaller molecule, because for smaller molecules it's easier to orient themselves to make the weak attractions. And on IMFs and bondings elements, you can do two problems. Take a pause here after you see what questions to do. So IMF and bonding, you can do (2018) number 4, and then the following one, 2018 number 2D, is on VSEPR, which you can do later. So for now, please take a minute, pause it, and do 2018 number 4. Okay, it is on IMF. So please do this problem, pause it, do the problem, and come back. Okie doke, welcome back, elements. Okay, now we're going to be on the last topic for Big Idea 2. Finally, this video will end. It is on VSEPR and MO theory. Remember, VSEPR help us tell the three-dimensional shapes. So you have to kind of identify your structure as A, B, E type and then memorize it and then go from there. But I'm going to show you or remind you here how to draw Lewis structures. We follow certain steps to make Lewis structures. Step 1, we count all the valence electrons in the system. Step 2, how many does it each need to be happy, except for hydrogen and helium, which are happy with 2, beryllium, which is happy with 4, and boron, which is happy with 6. Everything else needs total of 8 electrons. Then you subtract from 2 minus 1, divide by 2, that gives you number of bonds, and you draw your structure. If you get lesser bonds than minimum required, then you attach everything with a single bond, complete everyone's octet, and put the extra electrons on the central atom. When we draw SF4 structure, we get a AB4E molecule. Now what we need to see around central atom A, how many bonded and lone pairs we need? We need 4 plus 1, 5, which hybridization gives us 5 orbital, sp3d2. 1, 2, 3 plus 1, 4, sorry, sp3d. Now this has been phased out, so if you just wrote sp3, that is fine. Only sp, sp2, sp3 are in your curriculum. Other type of questions on VSEPR you get is, what is the hybridization on carbon 1? So you see how many either bonded or lone pairs around it, 4, so it is sp3, sp3. Around this carbon, it will be sp2 because double bond is just one electron domain. around this oxygen, it is 2 lone pairs. So 2, 3 and 4. So it is still sp3. Okay. MO theory, you just need to know the principle behind it, that electrons can behave as waves, and when waves travel through a 3D space, they interfere with each other. This interference could either be constructive interference or destructive interference. If they interfere with each other constructively, they form a bonding molecular orbital, which is lower energy, and if they destructively interfere with each other, they form a higher energy anti-bonding orbital. And then they will give you this structure. You just fill in there and you calculate bond order. Bond order is calculated by number of electrons in bonding minus number of electrons in anti-bonding orbital divided by 2. If you get 0 or a negative value, then that substance is not possible. If you get greater than 0, 1 or even a fraction, then that is a possible molecule. And that is the extent to which you need to know that. And at this point, elements, you can do question 2018 to 2D. Take a pause and do those questions. And this is your first video, and in second video I'll do big idea 3, 4, 5 and 6, but a lot of it has been phased out, so it will be a shorter video. Thank you. Oh wait, I haven't done the labs, so let me see if there are labs of big idea 2 that we did. Qualitative analysis, titration. PES lab, we did a dry lab, right? It was more like a worksheet, so please go reference it. Then we did an online VSEPR lab. It really didn't have a methodology or anything. You wrote for different molecules, what were their shapes and angles. And then you did molar mass of a volatile liquid lab, where you took a gas, evaporated it, and using Pubnert equation, we found the molar mass. We didn't do the IMF lab this year. Kinetics lab will be in the next video. I think that is all for this video. Thank you for listening, everybody. I hope you found this useful.